Welcome everyone to our today's webinar, Thermalconductivity Measurements of Thin Films. Sorry for the short delay. I had some technical issues. Hopefully you can see now my screen. Before we start now with the actual webinar, some organizational information for you. All of you participants are muted, and if you have any questions, comments, please use the chat or the so-called question and answer tool. However, all of your questions I will answer then at the end of the presentation so that there will be a moderated question answer session at the end of this webinar. As mentioned, if anything plops up, any questions or so on, please use the chat or the question answer tool. If you want to have a look onto the webinar later on, the webinar will be recorded. So the recording you can find then after the webinar in the chat, which you can download. Of course, we are also happy to receive some feedback after the webinar. If only of your questions, if you had any are answered, or if any are plopping up later on, or if you have any further feedback on our webinar series in general, please just contact us. We will be happy to receive some feedback. So before we move on, I also want to introduce myself. So my name is Erika Hahn. I'm working for Linsight for 4 years right now in the application laboratory, where I'm responsible for thermal conductivity and thermoelectric materials testing. And for those who do not know the company, I will also give a short introductions. Later on, we will having a look onto the thin film characterization. What are thin films? Where we start from the thickness to call it thin films and so on. And later on, we will have a look onto the methods we can offer to measure the thermal conductivity of thin films, which are the periodic laser heating, the frequency domain thermoreflectance, the thin film analyzer, and in the end, I will summarize that and give some examples on where this technology might be used to. So now the company introduction. The company Linsight Messgeräte was founded in 1957 by Dr. Maximilian Linsight, whom you see on the left upper picture. Now the company is led in third generation. First, it was owned then by Klaus Linsight and led by Klaus Linsight. Second picture here. And now the daily business is done by his two sons, so Klaus' two sons, Florian Linsight and Dr. Vincent Linsight. The main business field of Linsight is the production and the development of instruments for thermal analysis, thermal conductivity, and thermoelectric materials, so materials research in general. However, we also have some laboratories where we can offer some surface measurements in our instruments. Might be very useful if one has, for example, just 5 samples to analyze per year, so that a purchase is not relevant. We can also a service measurement for that. The development and the manufacturing is happening also here in Selb, but we also have some sales locations and service locations in the US, China, and India. And in addition to that, more than 65 distributors worldwide, so that in almost every country you have a contact person which you can contact regarding our instruments. On this slide, you can see our product range, ranging from the classical calorimetry, thermal analysis like calorimetry, thermogravimetry, or a combination in the SDA, up to dialectometers or thermomechanical analysis. We have a broad product range for thermal conductivity determination as well as for thin films. and can also analyze thermoelectric materials with also the investigation of Hall effects, both also from bulk to thin films. The unique part about Lean Size is the high level of options and customization which is possible. So, for example, one can have high pressure applications, very high temperature applications, hydrogens, gas analysis equipment connected to the instrument, and many more, so that there are a lot of different possibilities. First of all, we need to talk about what are thin films. So everyone defines thin films a little bit different. What we define as a thin film is a layer of a few nanometer to micrometer range. For example, films are grown on a specific substrate like glass or silicon dioxide, and many more. Um, Such growing techniques are, for example, PVD, CVD, or from the liquid phase, drop casting, spin coating, and printing. Furthermore, there are many different kind of films, so like semiconductor materials, especially also used in thermoelectric applications, sensors, or metallic films, mainly, for example, used as contacts, or to thin films belong also thermal barrier coatings or optical coatings, where the investigation might be necessary. And in addition to that, to the coatings, also thin films are, for example, freestanding films like polymeric films. Typically, they're in the lower micrometer range up to a few hundreds of micrometer range. More graphically shown, this is the general scale of thickness, starting from the subatomic range, going to the angstrom scale, and starting from the nanoscale to the macroscopic scale where we are working at. As for example, thermal conductivity, you can always only talk about that if one is in nanoscale, because below then there are just a few atoms and they typically don't interact regarding thermal conductivity. You already see here a little bit the separation, thin film methods with the TFA, FDTR, and PLH, where we will have a look onto, and for bulk materials, so macroscopic range for sure, and a little bit going down to the microscopic range, the LFA and THB are, for example, methods for thermal conductivity determination. As you see here, the PLH method is a little bit, crossing two parts here. So it's more or less just overcoming the gap from nanoscale, starting lower microscale, and reaching up closely to the macroscopic range. However, here this red rectangular shows what we call thin film. So nanometer, low nanometer range up to a few tenths of micrometer. More closely, you can see it here. So up to a few tenths of micrometer, we are talking about thin films, and the PLH method closes the border between the nanoscale and the microscopic or macroscopic range, and covers here both parts. But more to that then later on. First of all, I want to roughly talk about why there's even the need to measure the thermal conductivity of thin film samples, why we cannot use just the values which are determined for bulk materials, as this is much easier. The reason for that is that the physical properties of thin films differ from bulk material. For some materials, very significantly. For example, for gold, the thermal conductivity reduce to half of the value when going down to nanometer films. So that is why it is important to measure these properties, as they might be significantly different from the bulk material. The reason for that is, of course, the reduced dimensionality, and in combination with that, the boundary scattering is much more relevant compared to a 3D material, as within a 3D material, so a bulk material, you have more freedoms of flexibility and movement, where within a 2D material, boundary scattering is appearing more and thus having also an influence onto the thermal conductivity. As mentioned before, the thickness has an impact onto the dependence of thermal conductivity. So that when going down to lower and lower thicknesses, it might be even that the heat transfer mechanism can change. So mostly the heat transfer is done by phonons, so lattice vibrations or freely moving electrons, depending on the kind of material. One mechanism might be the more relevant or the more dominating one. And when changing the thickness, this relation might change, and this might influence the value of conductivity very much. Also, for thin films, the thermal interface resistance is more relevant, as interfaces or boundaries introduce thermal resistances, which have a much higher impact onto thin films compared to bulk materials, and that might change the properties as well. So for many materials, one can find out a thickness dependency and reduce transport properties, both in respect of electrical and thermal, so that not only the thermal conductivity is influenced, but also the electrical one, which shows the need of investigating a thin film. In combination with that, I want to mention that also anisotropy has an influence onto the measurement, or should be considered when performing the measurement, so that thermal conductivity can vary through or within the thin film material, so that it might be, depending on the direction of measurement, the properties will be completely different. For example, if one has a graphite fiber sheet, the thermal conductivity in plane, so in the direction of the fibers, is typically much higher compared to the through plane direction, so um, directional, so 90-degree angle to the fibers. The conductivity is much lower compared to the in plane direction, so this should be considered as well. This anisotropy might appear due to the manufacturing process, so on the deposition method, which changes the microstructure, or within thin films, the texture and the grain orientation in crystals becomes more dominating, or the effect of that is more dominating, and small defects might have a very intensive impact onto the thermal conductivity, where within a bulk material this would be, let's say, averaged more, so that it does not um, influence the behavior that much compared to a thin film. And basically, anisotropy just appears when the sample is very inhomogeneous. So I will also mention which of the methods we will have a look on measures into which direction of the sample. So as mentioned before, it should be considered when testing the material, which direction is tested, as this might have an influence. So now we start with having a closer look onto the different methods Linsize can offer to measure thin films. We start from the higher thickness and go down to lower and lower thickness. So now we start with the PLH, the so-called periodic laser heating instrument we offer, which is a very useful tool for freestanding foils in the micrometer range, so a few tens of micrometer up to a few hundreds of micrometer. The working principle is the following. So we have on the one end a modulated laser, which excites the sample with a modulated laser beam. And on the reverse side, there is an infrared detector, which collects the emitted infrared radiation. And at the end, we evaluate the signal. For those who are familiar with the laser flash principle, this might appear similar. It is indeed, it is a similar principle. The main difference here is the form of the laser light. Within the classical laser flash system, we have a time domain, time defined pulse of a few milliseconds shooting onto the sample. And we also collect the infrared radiation with a detector. Here, the difference is that we have a modulated laser light. The reason for that is that for thin films, the temperature rise curve has very low time scales, and that would require a even shorter laser pulse in the nanosecond, femtosecond range. And these lasers are technically very complex to build and very expensive. And thus we switch here for a simpler use to the frequency domain so that we have a modulation. These lasers are, let's say, easy to get and simpler to use. And this allows then the measurement of thin films as we don't need to um, have a look onto these short time scales anymore. So the signal we will get in the end is evaluated with a lock-in amplifier. What we record is the frequency of the laser, which we tune and have a look onto the phase and amplitude change. So we will have a signal like that, where IL is the signal of the laser with a certain frequency. IIR is the emitted signal of the sample. And we can clearly see here a phase shift of both signals and a change in amplitude. This is what we are looking for. We evaluate it in a special way. So here you see the logarithm of the frequency, and here a special evaluation. We do it to get that into a linear relation, as linear relations are easy to evaluate. And in the end, we are interested here in the slope of this curve. So in blue, we have a look onto the phase shift, and in green, we have a look onto the amplitude change. Out of both slopes, we can calculate each the thermal diffusivity for the phase change part and the amplitude change. Here also the sample thickness is considered. So similar to the classical laser flash, we need to measure the sample thickness before the experiment. The total thermal diffusivity of the material is used or calculated using both of these separate thermal diffusivities, so that the target property of the PLH is also thermal diffusivity of materials. As the method is very similar to the laser flash, we don't only find the basic method behind it similar to the laser flash, but also the sample preparation. So that we need to coat the samples with a thin graphite layer before the experiment to just have a maximized absorption of the material. And for example, in case of the PE foil, here you can hardly see the foil, and with the black coating, it is not transparent anymore, allowing a higher signal at the end of the measurement. Then the sample is placed into the sample holder. So we have separate sample holders for one sample and use such sample carriers up to 3 or 6 samples to be measured in the system. For those who know our classical laser flash system, they might recognize the similarity of the sample holder. This is not by chance. So here we use with the PLH the same sample holders as with classical laser flash, as there is the possibility to equip the classical laser flash with the PLH method. So that is also why here this picture is shown. So there is the possibility to have a PLH as an own system, but what is patented to have also a combined system with the PLH method and the classical laser flash method, allowing an extension of the application range. So measuring from thin films to bulk materials within one instrument. To close the PLH topic, I have here some applications. So here you see a PDFE foil or Teflon foil of thickness 100 micrometer, where we performed the experiment with sweeping through different frequencies. A sample shows a thermal diffusivity, total thermal diffusivity of 0.11 millimeter squared per second, which is pretty close to the literature value, which you can see on the right. Here you also can see the good repeatability of this number of measurements, where we are always close to the literature values and there is no significant fluctuation within the results. The result fit will also show the fit quality, which is here also quite perfect. For the evaluation, which is an optimized process, the part of this plot is used with the highest linearity. So at least 20 points should fit onto a linear line. Because some samples show some irregularities at higher or lower frequency, and this part we just cut out and focus on the linear section. Here you see a measurement of a higher conductive sample, which was sapphire with 500 micrometers approximately, and we got a thermal diffusivity of about 13 millimeters squared, which is also a very, very good agreement with literature and shows also a very good repeatability. So maybe to already quickly summarize, the PLH method is for thin films, freestanding thin films like polymer foils or ceramic plates, metals in the lower 10 micrometer range up to a few hundreds of micrometer. Coming now to the FDTR method, which stands for frequency domain thermoreflectance. This method is implemented in our so-called TF-LFA, so thin film laser analyzer. Before I continue, maybe just a short recap of the thermal properties which we're talking about. So starting with the thermalconductivity, which is the well-known property of the capability of a material to transfer heat in watt per meter Kelvin. And then there is the volumetric heat capacity, which is the product of the density and the specific heat capacity. There's the thermal diffusivity, so the end result of the laser flash or the PLH method, which measures how fast heat spreads through a material, typically in meter or millimeter squared per second. There's also the thermal effusivity, which is, let's say, a property which describes how warm a material feels. So metals feel cold. Um, polymers or insulation materials feel warm in the same surrounding, and that is captured with the so-called thermal effusivity. Also, a property which will be mentioned now on the topic of the FDTR method is the thermal boundary conductance. That is the ability of heat to flow across the interface or boundary between two contacting materials, so related to the contact resistance of materials. This slide should explain how this FDTR method works. First of all, we have here on the top right our sample. So the FDTR samples are typically coated samples, so multi-layer samples with a substrate and a thin film, which is marked red. And on top, the method requires to place in a thin gold reflective layer. With thin, I mean 60 to 70 nanometers. And this gold coating is needed as within this method it acts as a thermometer. We use with this method the reflectivity change of gold in dependence on temperature change. So with PLH or LFA, we detect the temperature rise over time with an infrared detector. And here we do the same with the gold layer and using the reflectivity of that. That means that we need samples for this method with a very smooth surface so that the gold layer will be like a mirror on top. For the measurement itself, we have two lasers, a pump laser, which is heating up the sample, so creates a local temperature change within the material. And then we have a probe laser detecting the change of reflectivity due to the change of temperature of the gold layer. So we have here a system including two lasers, one for the heat induction and the other one for detection. Important point here is that this pump laser is also frequency modulated. This we also do to avoid limitations regarding time scale. So here we can work independent of the time, more or less, as we are in the frequency range. The heat disturbance signal as well as the probe laser signal are both analyzed also in a lock-in amplifier. There we analyze the phase response, use a multi-layer model to evaluate the measurement, where we typically have to set up substrate, sample, and gold coating. Here we use a Gaussian distribution of the heat propagation to be able to measure multi-layer samples. That is how a typical signal looks like or evaluated signal looks like, where we have the phase response independence on the frequency. What we will get out of this measurement is the thermal conductivity, the thermal diffusivity, the volumetric heat capacity, and the effusivity. What we need prior to the measurement is some information about the substrate, conductivity of that, heat capacity and density of the thin film. We typically just need the sample thickness. As well, we need the thickness of the substrate and the gold coating, and out of that we can directly calculate the conductivity of the thin film. So that the FDTR method is a direct measurement of thermal conductivity of multi-layer materials with a thin film as a coating. Advantages is also that that it is a non-contact technique, allowing the characterization of a lot of properties of the thin film. On this slide, it is a little bit more summarized so that we have with the FDTR a pump and probe technique, two lasers, one for excitation and one for detection, where the probe laser, no, the excitation laser, sorry, is a modulated one. And here we sweep through different frequencies as well. We use the gold layer as a thermometer to detect temperature change on the sample surface, um, and use the frequency as a changeable parameter to detect the phase response with respect to the frequency. Out of that, with a multi-layer evaluation tool, we find out the thermal properties of the material, which are conductivity, diffusivity, volumetric heat capacity, and the effusivity. Here I have also attached some examples like silicon dioxide, where one can directly see that the thickness of the coating has an impact on the results. On the left, we have a measurement of a 285 nanometer layer of silicon dioxide, and on the right, about 500 nanometer. On the left, we obtain a thermal conductivity of about 0.2 watt per meter Kelvin, and on the right, about 1.5 watt per meter Kelvin, where we already can see a difference within the thermal conductivity. This investigation we can also do temperature dependent. So this example shows the measurement of the thinner silicon dioxide layer up to 200 degrees Celsius. The blue curve is the thermal conductivity, where we can see a rise of thermal conductivity with temperature. So that shows also the importance of performing the measurements also in the required temperature range, as the properties might change here also significantly. For a higher conductive material, I have placed here a measurement of aluminum nitride with about 200 nanometer. Conductivity is about 14 watt per meter Kelvin. And we also see here a good agreement between fit and model. If we go back, we see that the shape of the curve is completely different, just due to the completely different properties of the material. This measurement was also repeated on a thicker layer of 800 nanometers. There we get already a conductivity of about 39 watt per meter Kelvin. And last, the measurement of a 1600 nanometer layer of aluminum nitride. And summarized, we can see here the trend in this plot. So starting from 200, going up to 1600 nanometer of the same material, aluminum nitride, and we see a significant influence onto the conductivity. So starting from lower than 20 watt per meter Kelvin, going to approximately 40. And here's also a further example showing us a completely different shape here of the curve, obtaining a conductivity of about 33 watt per meter Kelvin, which in this case was molybdenum of 200 nanometer. Summarized a little bit here on the bottom, we have the literature values, and on the y-axis, the measured thermal conductivities ranging from glass to silicon, where we can see a good match between measured values and literature of different kinds of material. The last instrument I want to have a look on today is the TFA, which is our thin film analyzer. So as mentioned at the beginning, we started from the thicker layers of a few tens to a few hundreds of micrometer. The FDTR is based on a few hundreds of nanometers up to a few micrometers, and the TFA is measuring from a few nanometers to a few hundreds of nanometers typically. The concept is the following. We have a sample material which needs to be deposited into one of our prefabricated chips. Techniques to deposit the sample are, for example, PVD, evaporation, CVD, inkjet printing, drop casting, or spin coating, or spray coating. There are many methods which can bring on the sample onto one of our chips. The chip will be on the next slide, where you can see that on our measuring chip, there are, let's say, two functions allowing a complete analysis of the material. So on the one hand, we have a hot wire technique allowing us to measure the thermal conductivity and the specific heat capacity of the material. For the conductivity determination, we use the so-called 3 omega method. And on the other hand, the second mode the chip allows is a 4-point probe measurement to be able to determine the electrical conductivity, the Hall constant, and also the Seebeck coefficient, which means that with this measuring chip of the thin film, we can get a full analysis starting from thermal properties going to electrical properties and thermoelectric properties. So here you can see one of our prefabricated chips. It has approximately the dimension 10 times 10 millimeter. Here in the central area, there are two membranes where the sample is deposited to. Before the deposition, we mask, of course, the chip. There are different possibilities with a metallic mask or Kapton tape, depending, of course, on the method which is used for deposition. Next step would be the sample deposition, and later on remove the mask to have here the coated sample. So you can see here the difference between the empty chip and the prepared chip, where the sample is located on top of these membranes. Next step would be to place this prefabricated chip into the measuring chamber, and we have a lid with spring pins contacting here the pads on this chip. So as mentioned, there are two modes: thermoconductivity mode, where, for example, for the heating wire, we need those two pads, and those 4 pads surrounding this membrane are used for the electrical property characterization. And these pads are contacted here with the slit and the pins. So, as mentioned, the determination of the thermal conductivity is using a hot strip or hot wire technique with a joule heating, so that during the measurement, the hot wire acts as a heater and a temperature sensor at the same time. Out of the temperature rise, we can find out then the thermal properties. To be able to do that, we have to include this hot wire in a membrane. This membrane is already within this chip included. The membrane has a temperature limit of about 280 to 300 degrees Celsius, and that also limits then the temperature range of the instrument itself. As mentioned before, we are using a 3 omega measurement to determine the thermal conductivity, which is also belonging to the transient methods. And it is a differential measurement, so that we need to measure an empty chip before the actual measurement of the layer. With the thermal conductivity, one can go to the next step, for example, for a thermoelectric material, and to determine the figure of merit, the ZT value, and depending on the system setup, if it is equipped also with a magnet, one can also find out Hall properties. Otherwise, one can do thermalconductivity determination as well as electrical conductivity measurement and Seebeck coefficient. So that this tool allows the full analysis for the figure of merit of, for example, thermoelectric materials. For this machine, I have also included here two examples. On the left, there's a thermoconductivity measurement of bismuth antimony, and on the right of P.PSS, where both of the measurements show a temperature measurement or temperature dependent measurement, as well as a thickness dependent measurement, where one can see on both examples a reduction of thermal conductivity with a reduction of dimensions, so that the thin layers, the thinnest layers, typically show here the lower thermal conductivity, which might vary significantly between the different thicknesses. So now I'm already at the point to summarize different methods and explain a little bit more for which application which method is useful. So starting with the PLH method, it is a useful tool for freestanding samples in the range of a few tens to a few hundreds of micrometer. And one can use it, for example, for polymeric films, ceramics, or metals, or combinations of that. Unique is here that it can be combined with a laser flash or a xenon flash, so allowing a full analysis from thin films to bulk materials within one instrument, where one just switches the mode from thin to bulk materials. Advantages is the simple sample preparation. It is the same as for classical laser flash analysis, so the coating with graphite. Currently, the setup is designed to measure cross plane, or better said, through plane. The in-plane mode is upcoming probably by the end of the year. So that one can also analyze anisotropy within thin films. The target property of the PLH is the thermal diffusivity. With known CP and density, one can also find out the thermal conductivity, of course, but the main target is the diffusivity. The temperature range is currently from room temperature up to 300 degrees Celsius, so a quite broad temperature range as well. For thinner materials, so a few hundreds of nanometers to a few micrometers, our FDTR method within our TF-LFA becomes of interest. This tool is very suitable for multi-layer samples with a very, very smooth surface, so that the needed gold reflective coating is shiny as a mirror. That is the part of the sample preparation to coat the samples with gold. Advantages here is, of course, that complex sample structures can be measured due to the possibility of evaluating multi-layer samples. Currently, it is also a through-plane measurement. However, also by the end of the year, the in-plane measurement mode is upcoming, so also anisotropy can be measured with this method. A big advantage here is also that this tool allows the direct measurement of the thermal conductivity, but also can determine the thermal diffusivity, volumetric heat capacity, as well as the thermal boundary conductance for special applications of the thin film in a direct way, without too many informations which are needed in the beginning. And the temperature range which we can offer with this tool is from room temperature to 500 degrees Celsius, so covering the interesting temperature range for example, for semiconductors, which is one of the main applications of this tool. The last instrument we had a look on today is the TFA, the thin film analyzer. Um, Here we have the prefabricated chips, and the coating needs to be placed directly onto the chip. This is limiting a little bit the technique due to the sensitive membrane, which cannot withstand temperatures higher than 280 degrees Celsius, which also limits the temperature range. However, we can go down to lower temperatures, so subambient temperatures, down to liquid nitrogen temperature, almost liquid nitrogen temperature of minus 170 degrees Celsius. The typical sample thickness range is in the lower nanometer range up to a few hundreds of nanometer range. For the thermoconductivity determination, we use a 3 omega method. Due to the setup of the um, chip, it is an in-plane measurement. It's a true in-plane measurement. Um, Unfortunately, without the possibility to switch the mode to a through-plane measurement, so that with the TFA, typically homogeneous samples are investigated in the in-plane direction. Very advantages also for the semiconductor industry or the thermoelectric industry is that this tool allows a full analysis, starting from thermal properties like thermoconductivity and specific heat capacity, um, going towards thermoelectric properties like the Seebeck coefficient and the figure of merit, and with the possibility to also determine the Hall coefficient and all the relevant parameters like mobility, charge carrier concentration, and so on. Here you see then a summary of the application range of thickness and thermal diffusivity, where we can directly see that the PLH is targeting the higher thicknesses but can cover a very broad range of thermal diffusivity. The FDTR method is for lower thicknesses, covering also a very broad range for a broad range of thicknesses. And the TFA is starting for very low thermal diffusivities and low thicknesses. For low thicknesses with high diffusivities, going to higher thicknesses with lower diffusivities, where we have here in the middle this overlap between FDTR and TFA method, so that it belongs to the kind of material which method suits the best for the application. As already mentioned in the middle of the talk, mainly the application fields for this thin film investigation is the semiconductor industry, where the thermoconductivity knowledge should prevent damages during the manufacturing process by dissipating heat, or one can investigate the effect of doping and defects on the thermoconductivity, or use the thermoconductivity value as a quality control factor. So check the manufacturing processes using the conductivity as parameter. Also, thin films are often used in thermoelectric and photovoltaic devices, which should improve the efficiency of the conversion process, so the thermoconductivity should be determined here as well. Or having a look onto microelectronics or energy conversion systems. Um, with that, one tries to have more efficient heat sinks, which conduct the heat faster away from the electronics. Here, a hot topic is heat spreaders with a high conductivity, or the knowledge of thermoconductivity might help in the design of a device to increase the lifespan and optimize the performance, as well as, for example, in aerospace. Thin films are in general often used for the miniaturization of devices, make things smaller and lighter. For example, for aerospace, less mass is advantageous. And for optoelectronics, thin films with high conductivities are used to prevent, for example, thermal degradation, which increases the lifespan and also optimizes the performance. So these are typical application fields of thin films. So often these are coatings, freestanding thin films, um, or for example, semiconductors, which are mainly also coated samples. So at this point, I'm done with my presentation. I want to thank you for your attention and participation. And now I will give you some time to type in your questions if you have any. Um, Otherwise, I would also like to point out our next webinar, which will be in about 2 weeks, about our new laser flash analyzer, so our updated version, where we'll talk about what we have changed and how this influences the performance of the device. So if you're also interested in the measurement of thermal conductivity of bulk materials with the classical laser flash method, I will be happy to see you there again. So as mentioned, thanks for the participation.